When we test a language model on a static dataset, the performance often looks flawless. The model returns high accuracy scores, projecting an image of perfect computational logic. But that structural integrity is an illusion. Because static benchmarks like MMLU are public, models inevitably absorb the test questions into their training data, leading to saturated scores and widespread contamination. To counter this, the industry moved toward open-ended dynamic benchmarks. Platforms like GameArena crowdsource evaluation by asking human users to chat with two models and vote on which response is better. This introduces a different flaw. Human evaluators often mistake a model's stylistic vibe for true reasoning ability, rewarding detailed formatting and polite tone rather than the logic underlying the answer. This crowdsourced approach is also deeply inefficient. Because it relies on voluntary participation and unstructured chat, less than 5% of these conversations yield a useful evaluation vote. Researchers are left with two incomplete tools. Static tests measure memorization, while open chat measures style. Neither can objectively isolate a model's raw reasoning power. To solve for this, researchers developed GameArena, a structural alternative to open-ended prompting. The core mechanism replaces conversational free play with rigid, gamified rule sets that dictate exactly how the model must interact. The framework utilizes 3 specific conversational games to test the models: Akinator, Taboo, and Bluffing. In this system, human players aren't subjective judges. They are adversarial agents, forced to operate within the game's strict boundaries. This structure removes human preference from the equation. Every game ends in a definitive binary outcome. The model either wins by reaching the objective or it loses. By constraining the environment, the simple game becomes a precise stress test designed to isolate specific logic pathways. Each of these games is mapped to a specific type of logical reasoning. In the Akinator protocol, the model asks binary questions to deduce a secret object. This isolates deductive and multi-hop reasoning, forcing the model to synthesize information across multiple rounds to rapidly narrow the search space. In Taboo, the model must guess a secret word from vague clues, while forbidden from uttering the target word itself. This forces abductive reasoning, generating the most likely explanation from incomplete or fragmented data. In the Bluffing protocol, the model interrogates a human player to determine if a statement is a lie. This evaluates inductive reasoning, drawing a probabilistic conclusion based purely on empirical observations of the user's answers. Rigid game rules allow researchers to push models onto distinct cognitive tracks that can be measured individually. Simply looking at the final win-loss record isn't enough. The outcome tells us if the model succeeded, but it doesn't show the logic used to get there. To map that internal logic, researchers use a method called retrospective analysis. The process begins by freezing the live game timeline at a specific turn. While paused, researchers inject a hidden background prompt, forcing the model to reveal its intermediate thought process before generating its next public move. In Akinator, the model outputs a hidden ranked list of probable objects based on current clues. In Bluffing, it outputs its internal probability regarding the user's truthfulness on a shifting 5-point scale. This transforms a text generation task into a quantifiable time series dataset of a model's internal states. With these hidden internal states finally exposed, we can now apply precise procedural metrics to score the model's reasoning efficiency. This is the disparity ratio, scoring Akinator performance by measuring information gain. A high-quality question splits possible objects evenly, maximizing data. A poor question, eliminating just one option, results in a high ratio and low score. For the Bluffing game, researchers use Spearman correlation to track if the prediction smoothly converges toward the truth, while the hopping penalty flags instability by measuring how wildly the model's logic oscillates between consecutive turns. These formulas strip away the model's verbal fluency to expose the raw mechanics of its reasoning. Applying this framework to current state-of-the-art models reveals performance gaps that standard tests miss. This leaderboard tracks both game outcomes and the underlying procedural metrics for the top 5 models. Claude 3.5 Sonnet showed statistical dominance across the board. Compared head-to-head with GPT-4o, Claude demonstrated higher multi-hop recall and greater confidence in its abductive reasoning. At the bottom of the list, we see where internal logic starts to break down. Mistral Large struggled to adhere to the game rules or converge logically in the bluffing environment, resulting in a 0% win rate. On standard static benchmarks, these models often show nearly identical scores. Static tests hide these logic deficits. Rigid, gamified environments successfully expose them. Beyond the scores, this approach addresses the underlying data efficiency bottleneck. GameArena's open-ended model is inefficient, yielding only 4 valid data points per 100 prompts. GameArena captures useful metrics in nearly 87% of sessions. The gamified architecture naturally completes interaction loops, generating massive datasets of multi-step reasoning traces rather than simple subjective votes. Measuring human preference only measures how well a model can mimic a style. To measure reasoning objectively, we must move these models into rigid, mathematically trackable environments. By forcing a system to operate under strict constraints, we generate a transparent record of the internal steps it takes to reach a conclusion.